In this section, we'll be looking at inverse trigonometric functions. We know that a function can only have an inverse if it passes the horizontal line test. Here we have the graph of y is equal to sine x, showing us with two periods. If we were to draw a horizontal line, for example our x-axis, we realize that our x-axis or a horizontal line will cut our sine graph in multiple positions. So our sine graph as it is has no inverse function. If we were to however restrict our domain to negative pi over 2 to pi over 2, which gives us a range of negative 1 to 1, we can now define a unique inverse trig function for sine. And this unique trig function for sine is defined as y is equal to arc sine of x, or y is equal to the sine inverse function of x, where the arc sine of x means the angle whose sine is equal to x. If you recall from your regular algebra that when we have a function y is equal to, for example, sine of x, by interchanging the x and y, we get our inverse function. We can do that also for trig functions. So by interchanging the x and the y, we get our inverse trig function for sine. X is equal to sine of y. So this is an alternative method of writing the inverse function. Because we're interchanging the x and y, and our domain and range is our x and y value, when we interchange these, we also interchange the domain and range. So the domain for our inverse sine function would be negative 1 to 1, and our range would be negative pi over 2 to pi over 2. Please note that the inverse sine function of x is not equal to 1 over sine of x. Now let's look at the graph of our inverse sine function. Our inverse sine function, we said, was y is equal to the arc sine of x, or x is equal to the sine of y, since we're interchanging our x and y. Since we interchange our domain and range, and we know that the domain is from negative pi over 2 to pi over 2, we're going to use some values in between to determine our corresponding x value, or. So here, we know that the sine of negative pi over 2 would be negative 1. We know the sine of negative pi over 4 will be negative square root of 2 over 2, which is approximately negative 0.7. Here the sine of 0 is 0. The sine of pi over 4 is positive square root of 2 over 2, which is approximately 0.7. And we know that the sine of pi over 2 is 1. Now we can use this correspondence point to plot our graph and draw our curve. So we know when it's negative pi over 2, we have a negative 1. When it's negative pi over 4, it's negative 0.7, so approximately a little more than 1/2, negative 1/2. When it's 0, it's 0. When it's pi over 4, we have 0.7, so pi over 4, 0.7. And when it's pi over 2, we have 1. So by plotting our points, we have the graph of our inverse sine function. And we can use a similar method to find the graph of the cosine, inverse cosine function, and the inverse tan function. Here we're looking at our other two inverse trigonometric function. We have y is equal to the arc cosine of x, and we have y is equal to the arc tan of x. We can get a graph for y is equal to arc cosine of x by doing the same thing we did for the arc sine of x. We can see from our graph that our domain for our arc cosine function is from negative 1 to 1, and this is based on our original cosine function, which had a range of negative 1 to 1. The range of our arc cosine function is from 0 to pi, because our regular cosine function completed half a cycle from 0 to pi. So the domain of our arc cosine is from -1 to 1, and the range is from 0 to pi. For our arctan function, if you recall from our tangent function, it has two vertical asymptotes at -pi/2 and pi/2. Since we're inverting our x and y, our vertical asymptotes now becomes our horizontal asymptote. So we have horizontal asymptotes at -pi/2 and horizontal asymptotes at pi/2. By choosing appropriate values for between -pi/2 and pi/2, we can get corresponding values for x, and we can see that our domain for arctan function would be from -infinity to +infinity, since it's going all the way in this direction and all the way in this direction, or basically just all real numbers. Our range, however, is from -pi/2 to pi/2. Here we'll be looking at a few examples at evaluating inverse trigonometric functions. First example we're looking at is evaluating the arc sine of 0. Now, recall what we said earlier on, that the arc sine is the angle whose sine is equal to 0. So the angle whose sine is equal to 0 would be equal to 0 radians or 0 degrees. So our answer here is just 0. If we look at this example, we're finding the arc sine of -2/2. So here we're trying to find out which angle will give us a value of -2/2. If you recall from our inverse trig function, sine goes from pi/2 to -pi/2. So we know in our first quadrant, sine is equal to the square root of 2/2. Here, in the opposite direction, this would be -pi/4, which would be square root of 2/2. So our answer here would be -pi/4. Here, for our cosine of -1/2, we know also from our domain and range of the arc cosine function, the arc cosine function goes from 0 to pi. We know our cosine is negative here at 2pi/3 from our unit circle. So the angle who give us a value of -1/2 would be 2pi/3. Here we have our tangent. We're trying to find the arctan of the square root of 3/3. Going back to our domain and range again of our arctan. For arctan, we go from -pi/2 to pi/2. Since it's negative, we know it's going to be down here. We know when we have pi/6, here we have the square root of 3/2 and 1/2 for the cosine and sine. Dividing side by cosine, we get the square root of 3/3. Since this is negative, our angle must then be -pi/6. So -pi/6 would be our answer to this. Now we'll be using inverse trigonometric function to write an angle theta as a function of its sides, the opposite, the hypotenuse, and the adjacent. We know that the sine of theta is equal to the opposite over the hypotenuse. We know that the cosine of theta is equal to the adjacent over the hypotenuse. And we know that tan theta is equal to the opposite over the adjacent. To write our sine function, our angle, as an inverse trig function, we know from this that theta will be the inverse sine of the opposite over the hypotenuse. We know that theta from this one will be the inverse cosine of the adjacent over the hypotenuse. And from tan theta, we know that theta is equal to the inverse tan of the opposite over the adjacent. Here we're looking at two examples of writing using an inverse trig function to write theta as a function of its side x. Here we're given the adjacent and the hypotenuse, so we know we could use cosine theta is equal to 4 over x, since cosine of theta is equal to the adjacent over the hypotenuse. Since we're required to write an inverse trig function for this, we know that theta would be the inverse cosine or arc cosine of 4 over x. Here in this example, we're given the opposite and the adjacent. Since we're given the opposite and adjacent, we could use tangent. So tan theta is equal to x plus 1 over 10. To write an inverse trig function for this, we know theta is equal to the arctan or tan inverse of x plus 1 all over 10. So here we have our two answers. Those two problems.